The world ocean is the lifeblood of this planet. It supplies us with food and energy, mineral wealth and transport. It provides us with every second breath we take and is home to a large percentage of life on Earth. Our climate and weather are driven by the ocean. Every one of us relies on and is connected to the marine environment. As human population expands to exploit more of our coastal waters, and global changes affect the very nature of the ocean and how it functions, both below and at the surface, there's a growing need for us to understand how it works and how it changes through time. Forecasting such changes is now recognised as a crucial part of future ocean management, in much the same way that weather forecasting is part of our daily lives. Providing the means to take a wide range of data into computer models and use it to understand the ocean is operational ecology. Existing computer models that can provide longer-term predictions over wide areas do exist, but there's been nothing applicable for local seas over shorter timespans, the kind of information that's required by those who rely on the sea for livelihoods or who are charged to manage local marine environments. The OPEC project aims to fill this gap. Professor Icarus Allen explains.
The Operational Ecology project, or OPEC, was funded by the European Commission. Uniquely, it's created 4 regional modelling systems which bring together a range of models describing the physics, the biogeochemistry and higher trophic levels. Includes the assimilation of data and has the aim of providing better data products for the Black, Baltic and Mediterranean seas and the North East Atlantic.
OPEC aims to fill the gaps in ocean monitoring across the 4 sea areas by developing an approach using model simulations based upon real observations and measurements and assessments of existing monitoring such as shipborne observation, remote sensing and data buoys. Already, OPEC has developed the mechanism for providing near real-time synopses of ocean conditions as rapid environmental assessments. Hindcasts of the recent past to provide current data for discrete local areas, which is of immediate use. Via a unique tool for end users such as marine management authorities, government departments, coastal managers, NGOs and marine industries, the data are now freely available through a portal in the form of self-assembled maps and graphs for each area, or as raw data that can be further interpreted by users. Use of the portal and the data behind it is free to all users and it can be accessed via the OPEC website. The data portal provides model-simulated data for European seas, which can be looked at in a variety of ways, including ecosystem indicators and regional seas. Or you can look at it through European Marine Strategy Framework Directive descriptors, which is what we'll use as our first example. Let's say I'm interested in eutrophication. First, I'll bring up phytoplankton and see how that grows and develops in the North Atlantic. Immediately you can see here the data that's been retrieved. We can move the map around, zoom in and zoom out, or select a day from the past 20 years. We can also look for more information about the actual data, such as who provided the data, a background summary of the region, contact details of where I can get further information, and details of the models that we used and their skills. And very important is the level of confidence that the data providers have in their data. Now, I might want to compare what's happening to the nutrients, and to illustrate this, I'll use another feature of the portal and build a graph for what is happening in this smaller region here. We can select a time period, so let's choose what's happened this century, starting with the year 2000. Now, the growth of phytoplankton is affected by nutrients, so let's choose another indicator for the North Atlantic, say nitrate, and add that into the plot to see how the 2 indicators interact. The portal shows this quite clearly on the graph. The green is phytoplankton and the purple is nitrate, and by using this tool I can zoom in on any particular years of interest. What this graph clearly shows is that as the nitrate increases, it causes a bloom in the phytoplankton. The phytoplankton then use up all of the nutrients, in this case nitrate, which declines, followed closely by a decline in phytoplankton. Now, this has obvious interest for those involved in fisheries management, for example, but could have much wider applications. Having created this output, I can save it or share it with others who may be interested. But what's the future for OPEC? Icarus Allen again.
OPEC's modelling approach has been adopted by other projects, and from this first stage, future developments aim to expand predictions forward across seasons, so enabling future planning for stakeholders, ranging from fisheries to agriculture, and including those who are responsible for monitoring the environment for our enjoyment and health.